and gets turned into a carbonyl. Which, by the way, what kind of oxidizing agent is required for that? To do that kind of reaction, what do you need? What? NAD? Well, okay. What's the oxidizing agent? NAD or FAD? What is it? Come on, speak loudly. What is it? It's NAD. That's right. Let's get going here. All right. So, because it's just an OH group, that you don't need the power of FAD in order to do this. All right. So you do this oxidation, and now what you do is that is an sp2 center, and if this was not being done in an enzyme, you'd end up with an achiral mixture. Okay, because you can add from either the top or the bottom, because it's a flat planar thing. But because of the miracle of the fact that you're in an enzyme, you come in specifically, you add the hydrogen back on from the top, and that pushes the oxygen down to the bottom. So, what you do is you have now successfully turned galactose into glucose. Aren't you thrilled? Okay. So first you do an oxidation, and then you do a reduction. All being done by the same enzyme. So, you start off with it up, and you end up with it down, and now you can get happy and go merrily along your way. Okay? Now, the enzyme that does this has a really cute name. You can almost imagine one of those old British actors saying it. One of those old guys in old British movies. This is called an epimerase. Yes, it's an epimerase. See, can't you just imagine some guy, old actor saying that, Richard Burton or something? The guy played, can't you, Jean-Luc Picard, Patrick Stewart said this. Number one, use an epimerase. All right, so I had to point that out. This is also the answer to one of the questions on the old test. Okay. All right, so there were two key things I wanted to bring out here. One, the reason galactose doesn't work is because the OH group in the 4 position is aimed the wrong way. That means if you got a sugar, any sugar, it has an OH group on the 4 carbon aimed this way, to this side. Which makes no sense on the recorders, of course. Okay? If you're looking at it, it's on the left, okay? If you got an OH group on this side in the 4 position, you have to use an epimerase in order for it to work. Any sugar that's got an OH group here, whether it's a ketose or an aldose, it will not work. You have... This is bad. That OH group has to be on the right. Has to be on the right. And the way we fix that problem in your cells is we use an epimerase to flip this from this side to that side. In the absence of an epimerase, wouldn't happen. Okay, so an epimerase in general, by the way, is an enzyme that converts the chirality. It flips something from one isomer to the other, like R to the S. So if something's pointed up, it aims it down. If something's aimed to the left, it turns it to the right. Okay? Keep that in mind when we get to question whatever it is. Question number 4. Okay. Now, having said all that, let's go over this thing. Everybody's next to someone who's got a copy. We're not going to have to rearrange the class like we did the first time, right? All right, everybody's next to somebody. Everybody can see one of these. All right, which of these does not use, here we go again, B. Actually, the answer is not B here. Because this isn't the first exam anymore. I'm not going to tell you. I have something else planned for extra credit for this one. There is an extra credit question that almost no one in here could get wrong. Alright, which of the following reactions does not, now you got to notice the not, see it's in all capital letters, that's what make it clear, use or make ATP. Because y'all had some reactions that made ATPs, right? Alright, the first one of these is simply taking glucose and turning it into glucose 6-phosphate. Obviously, we talked about this more than once. That obviously uses an ATP, right? What kind of enzyme does this? It's a kinase. And kinase either use or make ATP. Remember, we had some that make it. So that one uses it. So that ain't the right answer. Okay? The second one of these, was PEP, going to pyruvate. This also involved a kinase, but what was special about this baby? It was so special. Okay. What's special about this one? Actually, I got these backwards. What's special about this one is we took a phosphate from this guy and gave it to an ADP. So we made an ATP. Okay? So that ain't the right answer. The third one of these, the third choice, was fructose 6-phosphate going to fructose 1,6-biphosphate. That was our great enzyme, PFK, phosphofructokinase. Okay? And obviously, that would use this has one phosphate, that has two. So the phosphate had to come from an ATP. So that took care of that. And so, and then I got backwards also. We've got dyslexic ATPs here. Okay. All right, so that doesn't work. Oh my God. We're narrowing it down now. The fourth one. The fourth one, as I'm going to point out, could be used as a trick answer for other things. The answer is D. The answer is D. Because what that enzyme does, what happens there is, actually, it requires a couple. What happens there is the starting material, the glycerate, gets attacked by the enzyme. Sulfur, okay, comes up and attacks this guy. Does a nucleophilic attack, which happens to be the answer to another question. And we made this. Okay? And then an NAD came along and took that, and that pair of electrons went there. And we made that, right? Okay? And that's an oxidation. By the way, that's an oxidation reaction. We went from an aldehyde to an ester kind of function. And then how did we free this up? With a phosphate coming in and attacking. And that is what made the product. See the ATP around anywhere? If I see any ATP